Hey, welcome back everyone, and today we're going to be working on the greedy questions from the LeetCode roadmap. So today we're going to do the first four questions, and the idea behind greedy questions is that we're going to be looking for the local optimals at every point. So when we have the local optimal and this converges into the global maximum or the optimal at the very end, then we can use a greedy approach. Otherwise, we usually have to resort to a DP approach. So let's start off with the first question, maximum subarray. So in maximum subarray, we're given an integer array nums, and we want to find the subarray with the largest sum and return the sum. So for example, in example 1 here, we're given -2, 1, -3, 4, -1, 2, 1, -5, and 4. So the subarray with the maximum sum, remember subarrays, they have to be continuous or contiguous. So the maximum subarray in this case is we start off with the 4, and then we go all the way until the 2 and the 1. So this, although there's a -1 here, this still sums up to 6, which is the maximum subarray in this case. If we include the -3, for example, then we're going to be more negative, so we don't want to include it. And including more numbers on either side of the subarray is going to cause the answer to be more negative. So looking at example 2 here, we only have a single number, it's positive, so we include it, and the answer is going to be 1. In example 3 here, nums is 5, 4, -1, 7, and 8. We can just include every number, because if we include -1, that means we can include the numbers on the left side and the right side. So we want to include both of those because they sum up to be greater than -1, so we just add everything together, which gives us 23. So in this question, we want to find the globally maximum subarray. So instead of looking at the globally maximum subarray at a single time, we can just look at the current maximum subarray, and then always compare with the global to see if we found a larger one. So let's create two variables. First one is global max. This is going to be the global answer, which we're going to return at the end. So let's set that to be the minimum. So float -infinity. And then we should always keep track of our current sum. So for example, if we start off from the left side going to the right side, we start off with -2, then we can add 1, -3, and so on. So current max is going to be the same thing. So -infinity, forgot the negative sign here. So now for every number, we can go from left to right. So for num in nums, now we're given num. So for example, -2. So we need to include the current number in our current max because it's the current maximum. So, however, current max, for example, if current max is negative, for example, we're at the index 1, we have the number 1, but the previous current max is going to be -2. So we have two options at this case. We can either take the -2, add a 1 to it, so we're at -1, or we can just completely discard this -2 and just start at the current index. So we know that in this case, starting at the current index gives us 1, whereas if we kept the previous current max, that's going to give us -1, because -2 plus 1 is -1. So we want the maximum of those, which means we're going to keep the number at the current index and just have the subarray start from here instead. So our current max is going to be the maximum of the two choices. The first choice is going to be keeping the previous one, so cur max plus our number num, or we can just use the number num and start the new subarray from here. So now we have a current subarray sum. Now we want to compare our global sum to the current sum. If the current one is higher than the global one, then the global one should be set to the current one. So we can do global max. Global max is going to equal max of global max, or our current max. And in the end, because the global max has compared to every subarray, and every current subarray is going to be the maximum at every index, that means we have found the globally maximum subarray, and we can just return that. So let's return global max. Let's try running that. Cool, so that worked. Let's submit it. Nice. So this question, if you guys didn't know, this algorithm is called Cadane's algorithm, and essentially it's a greedy algorithm that compares the current max at every possible index, and at every index we want to see if we want to keep the previous current max and append to it, or just start a new one from the current number. So for every index, we know the maximum continuous subarray that ends at that index. And because the globally maximum subarray has to end at some index, we just compare that, the current max, with the global one. So we update the global one to be the largest one, and we iterate throughout the array so we know we must have seen the global one sometime. So in the end, we just return global max. So that's this question, and that's Godin's algorithm. So let's move on to the next question. Jump game. So in this question, we're given an integer array nums, and initially we're going to be positioned at the array's first index. So we're going to be here at index 0, and each element of the array represents the maximum jump length at that position. So we want to return true if we can reach the last index, or index n-1, or false if we cannot reach that. So in example 1 here, we start off with index 0. This being 2 means that we can jump a total of 2 distance, so we can jump to the 3 or the 1 here. So this question, it's more optimal to jump to the first index because that gives us a jump distance of 3. Then from this index, we can jump to the next one, the one after that, or the final one. So we want to output true because it's possible to reach the last index, and that's what we want to return. So in example 2 here, at the start, we can jump 3 distance, so 1, 2, 3. At the second index, we can jump the same. Third index, we can still jump every index, essentially we can jump to this index here, 0, 1, 2, 3. But at index 3, the jump distance is 0. That means we cannot jump to the last index no matter where we started. So we always fail and we're always stuck at index 3. So this question, it's impossible to reach that last index. It's impossible, so we want to return false in this case. So in jump game, this is a greedy question because at every index, we can just look at the maximum range that we can jump to. So for example, the 2, our range is going to be 2 plus 1, so the 3 here, or the 1 here. So we cover this entire range. And then inside this entire range, we can look at every jump distance in this range, so the 3 and the 1, and then we calculate the next range from there. So because this is a 3, that means we can jump 1, 2, 3. So this becomes our new range. So we always want to look for the maximum range that we can find in the previous range, and then that is going to be the next range we test. Eventually until we find the very last index, in which case we can return true, or if we don't find the last index, then we want to return false. So if any range is not going to increase our range, for example, these 3 numbers here, it's not going to increase our range because they're all stuck at index 3, then in that case we want to return false if we're stuck at the same range for more than one time. So at the start of the question, we're starting on index 1 or index 0, so we can set the L and R are the left and the right bounds of our range, and they're both going to be 0. So now we're going to repeat this next range finding process. So let's do a while loop. So while true, we can look for the next biggest range. So next range, we're going to look for the right side of the next range because we know the left side of the next range is always going to be 1 plus r. So for example, if our range is 0 to 0 here, then the next range is going to start at 1 after that. So all we care about is the next r. So next r, we can just set that to 0 at the start. And now for every number in the range, so for I in range from L to r plus 1, because the second parameter is going to be non-inclusive, so we want to do r plus 1. We want to compare new r, or next r, is going to be equal to the maximum of the next unlocked range. For example, if we're at index 1 here, we can jump a distance of 3. So the maximum value of the next r is going to be the current index it's at, so index 1, or it's going to be I, in addition to how many distances we can jump. So this is going to be 3 in this case, which is nums at I. So, or if it's smaller than xr is just going to be itself. So now after that, we want to look at if we reach the final index. So if next r is greater than or equal to, the final index is going to be n-1 or len nums minus 1. So if we reach the final index, we can just return true. We don't have to search anymore, so return true. However, if next r is going to be less than or equal to the previous r, that means we weren't able to expand the range. And that is because we reached something where the range is 0 and we can't get any further. So if we're stuck at here for more than one iteration, we can just return false, because searching more will do the same thing. So return false. After that, we want to update our range. Remember, the new L is going to be equal to 1 plus the previous range's right. So for example, if we were 0, 0 at the start, the new left is going to be 1 plus the right. So L equals R plus 1. And R is just going to be equal to the next R. After that, we can just return, it doesn't matter what we return because we return true or false inside the loop, and that's going to determine. So we can just return false. Let's try running it. Cool, that worked. So let's submit it. Nice. So this question, jump game, is pretty classic. It's going to be a greedy question because we're always looking for the maximum place we can jump to. And that's all we care about. We care about how far we can jump, the maximum one. And then we search for every number in that range to look for the next largest or next maximum jump, all the way until we reach something where we cannot jump anymore and we're stuck at the same range, or we reach the final one, in which case we can return true. So let's move on to the next question. Jump game 2. So in this question, we're given the same zero index array of nums, length n, and we're initially positioned on nums 0 again. So each index, nums I, represents the maximum distance forward. So again, just like before, if we're at nums I, we can jump to any nums I plus j. Except in this case, it's going to be less than n. So I plus j is never going to be out of bounds. And we want to return the minimum number of jumps to reach nums n minus 1. And the test cases are generated so we can always reach n minus 1. So we don't have to worry about returning false in this case. So in this question, we're given similarly a array, and we want to see the minimum number of jumps to jump to the last index. So this test case is actually the same as the previous one, I think. So the first jump is going to jump to index 1, then we jump to the final index. That took 2 jumps, so we output 2. So in example 2 here, 2 and 3 are the same. So again, we jump to index 1. Index 1 lets us jump 3 times, so we jump to the final index. So just like the previous question, we can set up looking for the next range. So starting with left and right equal to 0 and 0, then we can set out to look for the next range, find the maximum one, the next range unlocks, and then look continuously. So every time we find a new range, we're going to have to increase the number of jumps by 1. And in the end, we can just output how many jumps we did. And that's going to be the number of times we searched different ranges. So we should keep track of that. Let's call that jumps, and jumps is going to be initialized to 0. So now let's do the same while loop, while true. We look for, first of all, we should check if we've already hit that range because it's possible nums, in this case nums is greater than 0, but it's also possible we hit the last index. So if r is greater than or equal to len nums minus 1, because if length of nums is exactly 1, that means we've already at the last index, in which case that took 0 jumps. So in this case, we want to just return jumps. Jumps is the number of jumps. If not, then we want to do the same process as the previous question. So we're going to initialize a new range or next range. This is going to be initialized to 0. Now for I in range of our current range, so it's going to be from left all the way to r plus 1 because non-inclusive. We look for the next r, and next r is going to be equal to maximum of how far we can jump from the current index. So starting from the current index and the number at the current index representing the distance we can jump. So it's going to be max of I plus nums I, just like the previous question, compared with next r, whichever one is bigger. So after this, that means we search this entire range. We're going to increase jumps by 1. Because to use the next range, we have to have jumped at least once. So now L equals to R plus 1, just like before, and R equals to next R to update our range. Now after that, we can just return. It doesn't really matter what we return because we're always going to be returning from here, since the question says the test cases are generated so that we can always reach the last index. So let's try submitting the question. Cool, that worked. Let's try running it. Nice. So this question basically follows the same code structure as before. The only difference is that we don't have to check if we cannot reach the answer because the question says we can always reach the final index. Another thing is that we have to keep track of the number of iterations this for loop or this while loop has gone through. And for every iteration, we want to increase the number of jumps by 1. Whenever we reach the final index, if r is greater than or equal to the final index, then we just return how many times this while loop iterated. And that's going to be the number of jumps, or the minimum number of jumps we have to have taken. So let's move on to the next question. So this question, gas station, we're given n gas stations along a circular route, where the amount of gas at the ith station is going to be gas at I. So we have a car with an unlimited gas tank, so basically an uncapped gas tank, and it costs I to travel from the ith station to the next one. And we begin the journey with an empty tank at one of the gas stations, so we can immediately fill up at that gas station. And we're given two arrays, gas and cost. They represent the gas and cost at every station. So if we can travel once around the circuit in the clockwise direction, so basically from the left to the right, and if we reach the end, then we loop back to the start. If we can travel once around the circuit, then we want to return the index that we started at, otherwise we want to return -1. So if there exists a solution, it's going to be guaranteed to be unique. So let's look at the example here. In example 1, we're given gas 1, 2, 3, 4, 5 and cost 3, 4, 5, 1, 2. So we want to start at gas station 3, or index 3, which is going to be the 4 gas here. So at the start, we fill up with 4, then it costs 1 to travel to index 4, so -1, but then we get to fill up 5 gas at index 4. So it's going to be 4 minus 1 plus 5, we have 8 units of gas. After that, we're going to loop back to the station 0, so we have to spend 2 gas to get there, but we do fill up 1 gas. So our gas decreases by the cost, but increases by the station, or the amount of gas at the station. So essentially we repeat the process and we make sure that our gas is never 0 or less whenever we travel. So for example, in example 2 here, the amount of gas is going to be 334, the cost is 343. So immediately we know that there's 10 cost, but there's only 9 gas. That means we cannot travel once, because to travel once we have to have filled every possible gas, and we have to have spent every possible cost. So if the number of gas, or the amount of gas, is less than the amount of cost, then it's going to be guaranteed to be -1, or it's impossible. So let's code that immediately. So first of all, gas total is going to be sum, so sum just sums up the array in Python. Sum gas, and cost total is going to be sum cost. So we know that if cost total is greater than gas total, then it's impossible to travel once around the circuit. We want to return -1. However, if cost total is equal to or less than the gas total, then it can be mathematically proven that the cost, or it's possible to travel once around the circuit. So I'm not going to go into the proof for the math idea in this case, it's an inductive idea, but instead I'm going to talk about how to code that algorithm to find the optimal starting position. So we know that if we start somewhere, for example 1, then the cost is 3, we're immediately going to be at -2 gas. So that is not a valid starting position. So if we start at 2, then we go to 4, it's also going to be negative. So we know that starting position, the gas has to be greater than the cost. But is that enough necessarily? No, because it's still possible to go negative later on. So for example, if we start at the 5, 5 is greater than 2, so gas is greater than cost at the current station. But if we go to the next station and the next one, so the next station we're going to lose 1 gas because we spend 2 but we get 1. Then the next station we're going to lose 2 gas because we spent 4 and then we gain 2. Then we're going to spend 5 and then gain 3, and that's going to make us go negative. So, or it's going to make us go to 0, so we're never going to make a full circuit. So we're going to look for a gas station that is going to allow us to go a full circuit. Now let's keep track of how much gas we have, so let's call that tank. Tank is going to be 0 at the start, and we should also keep track of our starting index. So which index do we want to start at? That's going to be what we return for the question. So start, this is going to be initialized to 0. Now for every gas station in the range of gas stations, we're going to check if we can travel from the current gas station to the next one without going negative. So for I in range let gas, so at every gas station, first we can fill up and then we're going to spend the amount. So first we do tank plus equals to gas at I. After that, we can do tank minus equals to cost at I. This is going to be the cost of going to the next stop. So we're going to preemptively subtract this from the tank. So if tank is going to be less than 0, that means we have a problem. We cannot travel to the next one. Because if tank is equal to 0, that means we can barely make it to the next one. But if tank is less than 0, that means we have a problem. So if tank is less than 0, that means we definitely don't want to start at this index. But which index do we want to start at? Can we start at the next index? Well, we shouldn't start at the next index, because we know that if we travel from that next index all the way to index I, we're eventually going to be negative again. Since we know at the start, the first index is not going to be negative. So for example, if we started at index 1, it's going to be negative because we hit a cost 3, 1 minus 3, that's going to be negative. But suppose this wasn't negative, but it's the next gas station that caused us to be negative. Then we also don't want to start at the next gas station. So essentially, we don't want to start at any gas station between start and the station I, which caused us to be negative. So the one we actually want to start at is going to be I plus 1. So start equals to I plus 1. Every index on the route from start to I is going to cause us to go negative. So start equals I plus 1. That means we want to avoid this pitfall. We don't want to go negative. And then we should reset our tank, because the tank is always going to be 0 at the start of our journey. So now after finding this entire for loop, basically we make sure that at every index, if it's possible to go negative, we don't want to start at it, and we want to start at the next one. And because the answer is guaranteed to be unique, we can just return start. So let's try running that. Cool, that worked. So the actual tricky part to this question is proving why it works when cost total is less than or equal to gas total. But that is going to be a math question, and it's not really in the scope of this greedy algorithm. So I could cover that potentially in a future video. But however this code works, so let's try submitting it. Cool, that worked. So this is the first 4 questions in the greedy algorithms section. We're going to create a new video for the next 4 questions to finish up all the greedy questions in the LeetCode roadmap. So thank you guys so much for watching. Hope you were able to learn something, and I'll see you in the next video.